Welcome, and thank you for joining our final round demonstration. I'm Julian Rocco, Laboratory Lead and Lead Systems Engineer.
And I'm Luke Lawson, Lead Systems Engineer and Digital Engineer.
We are members of the Student Space Programs Laboratory at Penn State. The next hour, we'd like to show you the Reclaim Digital Twin. Not describe it, show it. Live. First, the name Reclaim stands for Resource Extraction and Conversion of Lunar Anthropogenic Input, microwaves. In plain terms, it's a machine that takes the waste a habitat produces, like scrap metals, discarded plastic, turns it back into usable material. The physical prototype is built around a single solid-state microwave generator, and that one generator is time-shared between two processing paths. Metals path that melts aluminum and other metals, situ ilmenite. Plastic path that breaks down plastic and other pyrolyzable materials. Um, this process is done within an inert atmosphere until it decomposes into volatile gases that can be used as fuel precursors. What we're presenting today is a digital twin of the machine. I want to be upfront about what we mean by that, because today, a digital twin is a term that gets used loosely. What you're going to see is not a picture of the machine, not a dashboard bolted onto raw data streams. It's a live, physics-based correspondence between the machine and a model. It understands how the machine behaves, deeply enough to predict what it's going to do, does it.
Here's the roadmap for our hour together. We'll start with our vision and what we believe is genuinely new here. A twin built is a reusable architecture running on a platform called Convened Systems. Then we'll walk the architecture end to end, and as we describe each piece, we're going to show you that piece live. The real edge computer, the real cloud engine, the real model. Then we'll stay in the live system and run 3 full scenarios. The nominal recycling scenario with Reclaim and the twin talking to each other in both directions, 2 off-nominal scenarios defined by NASA, the lunar surface scenario, which is a condition no Earth prototype can ever be physically tested in, and a power outage scenario, where the system experiences a complete loss of power for 5 minutes. We'll close with what the twin gives the engineering program and how it's verified. If you keep one thread in mind for the whole hour, make it this one. Everything you're about to see is one model, one source of truth, running live in front of you.
Our innovation runs on two sides at once, and it's worth taking a moment on each. On the system side, the twin is a complete engineered system in its own right, with its own architecture running end to end. Telemetry originates on the machine's controller, a compact Rio, which is an industrial real-time controller from National Instruments that actually operates the hardware. That telemetry flows to a Raspberry Pi, acting as an edge gateway. Pi pushes it securely up to the cloud, and it lands in Convene, a hub where everything comes together. Typeline isn't a one-off built for a demo. It's a reusable pattern that works for any engineering system whose behavior has real uncertainty in it. On the tool side, Reclaim is the very first full deployment of Convene, cloud-based digital twin platform. And here's the problem. Convene exists to solve. Conventional practice produces 3 separate artifacts that start drifting apart the day they're created. A systems model in one tool, simulations in a second tool, and a dashboard in a third. 6 months later, nobody's sure which one reflects the real machine. Convene collapses those into one maintained digital thread. The systems model, written in Object Management Group's SysML version 2, which is being deployed as a next generation models-based systems engineering within the industry, serving as the model of record. The live estimator and forecaster are predictive engine, and an error correction layer learns whatever the physics doesn't capture. One thread, one truth. Existing twin technology serves predictable, well-behaved systems. Reclaim is aimed at the harder problem, systems with genuine randomness in their behavior, and that's the gap we close.
To be fair to the state of the art, industry already hosts cloud based thread connected twins. Siemens, Nvidia, and Amazon all have serious offerings. We're not claiming to have invented the category. What we've added are 2 things those platforms don't put together in one place. First, a verification loop that is closed and continuously evaluated. The system is always checking itself against its requirements live, not at milestones. and second, a physics-based predictive estimator at the core. The twin doesn't just mirror the machine, it forecasts it. And we did it on a stack a student team can actually build and afford. The commercial story follows naturally from that, and it's worth being direct about who buys twins shaped like this one. Defense and industrial sustainment programs already procure exactly this pattern: condition based maintenance, fleet health monitoring, predictive readiness. Twins whose jobs is keeping critical systems alive and efficient, not rendering them. That's the discipline we've built, and lunar surface infrastructure needs it for the same reason a deployed fleet does. The hardware is remote, critical, and irreplaceable. Convene is the reusable platform. Reclaim is its flagship use case. The proof it works on a real, messy, high powered piece of hardware. The same architecture transfers to any multi domain engineering system with uncertainty in it: defense systems, aerospace test programs, process manufacturing. The estimator stack, the common filter, the forecaster, the learned error model runs as ordinary cloud services, fed by that Raspberry Pi gateway and bound to the system's model. The point is this: was usually a one off deliverable that dies after the program review, we've turned into shared infrastructure that outlives it.
Now, the complete architecture. And this is the heart of the whole story. So let's take it slowly. There are three load-bearing pieces: machine-readable sign in the systems model, written in SysML v2, every requirement, every component, every interface, in a form software can read and check. The predictive engine, physics and estimation software, runs on the dedicated cloud virtual machine. And, finally, a digital thread ties the two together, binding live data to model elements and requirements by name. Now, follow a single measurement through the system. It's born on the CREO controller at the machine. It travels to the Raspberry Pi at the edge. The Pi pushes it over an encrypted connection up into Convene, the hub. Convene routes it out to the predictive engine on the cloud machine. The engine turns raw readings into estimates, forecasts, and advisories, and those flow back into the same hub, where the thread binds them to the model and its requirements. Convene is the single source of truth. Data is born at the edge, enters the hub, gets processed, and returns to the same hub. Nothing lives in three different copies. And one detail we're proud of because it matters more than it sounds: every frame of telemetry carries its own timestamp, so the engine runs on the telemetry's clock, not the server's. That means the physics is computed on the machine's own timeline, which is what makes everything you'll see later, including running scenarios, faster than real time, honest.
This is how a machine joins the twin. The edge computer here, which is the Raspberry Pi, is wired to the machine's controller. It introduces itself to Convene with a one-time pairing code. Enter the code in the hub and the machine gets an identity. Not just a connection, an identity. Every message it sends from now on is authenticated as this machine. And the moment the pairing lands, watch as the variables begin to flow in. Everything you've seen so far runs on one systems model. This one for our program is written in SysML v2. In these few diagrams I'm showing our base level architecture from system broken down into subsystem with various key subsystems outlined, specifically the metals, pyrolysis, predictive engine, and cloud architecture. These are all defined in the same model, not in separate documents. And this is the part that matters. The requirements live in here too. They're bound by digital threads that actually make the requirements live verifying as the system runs real time. This is our differentiator.
And everything you just saw is reusable by construction. Nothing in the path is specific to Reclaim, except the physics module in the middle. Any edge device publishing into the hub, any model service on the cloud, the same threads, the same dashboards. That's the product thesis in one sentence. This architecture transfers to any engineering system whose behavior carries real uncertainty. You swap the physics, and the rest of the machinery comes with you.
Let's open up the engine itself because this is where the twin earns the word predictive. At the core is a physics model, a two-node energy balance. It's a fancy way of saying we track heat in two places: the reaction bed at the center of the chamber, where the microwaves deposit their energy, and the chamber wall around it. Every energy comes in from the microwave source and is absorbed by the reaction bed or crucible, which permeates throughout the chamber. And we integrate those flows forward in time with a standard high accuracy numerical method. The bookkeeping is tight. Energy is conserved to better than 200th of 1%. On top of the physics sits an uncensored Kalman filter. If that term is new, a Kalman filter is an algorithm that blends noisy sensor readings with a physics model to produce a best estimate of the system's true state, including states you cannot measure directly. Ours recovers a hidden quantity that matters enormously in this machine: how strongly the bed is absorbing microwave energy, which changes as the material heats. No sensor measures that. The filter infers live. Alongside that, a Gaussian process, a statistical model that learns patterns from data, captures whatever error remains between our physics and reality. And this is important. It's evidence gated. It only corrects where it has seen data. Anywhere else, it steps aside and pure physics carries the prediction. The learning is bounded and it's never load bearing. Finally, the same data stream computes the challenge's scored performance metrics: mass efficiency, energy efficiency, thermal margin, cycle time, live with full traceability. The pipeline end to end. Ingest the telemetry, estimate the state, forecast ahead, advise the operator, compute the metrics, publish everything to the hub.
A fair question for any model is, how do you know it's right? Our answer is that fidelity is not fitted, not asserted. Our answer is that fidelity is fitted, not asserted. Every coefficient in the model starts from somewhere defensible. Geometry measured from the as-built CAD assembly, 135 parts of it, and material properties from published literature. That gives us heat loss surface areas of about 0.29 square meters on the plastic chamber and 0.42 on the metals chamber, and the heat capacity is computed from the actual part volumes. Then a calibration pipeline refers these starting values against log cycles from the real machine. Engineers call this a gray box model. The physics provides the structure, the data tunes the constants, and the result is accurate where we have evidence and honest about itself where we don't. The two chambers are modeled separately because they're genuinely different machines. The plastic chamber has a SiC bed and stainless steel walls with hard temperature sealing. The metals chamber has a SiC crucible, a material that absorbs microwaves and converts them to heat. Plus, the physics of melting aluminum and pyrolyzing plastic carries its own register of parameters.
Let's talk about where the data actually comes from, because a twin is only as trustworthy as its measurements. The CRIO controller runs the machine's control software in LabVIEW and logs everything at 500 Hz. A lighter stream, 5 to 10 frames per second, each stamped with a standard timestamp, is what travels to the cloud. And as we said, the engine integrates on that telemetry time. The as-built sensor suite includes 4 thermocouples tack welded onto the reaction chambers, an infrared sensor providing additional readings from the metal chamber, thermocouples on the condensers, pressure sensors on the chamber and downstream line, pump status flags, and one shared measurement of forward and reflected microwave power. Two honesty points here. The metal's chamber wall temperature is not fully instrumented, so the twin estimates it. That's the Kalman filter doing exactly what it exists to do, recovering a state we can't afford to measure. And the masses that feed the scored efficiency metrics are weighed by NASA and entered by the operator, with that provenance recorded. Where sensor exists only on the piping diagram and not yet in the hardware, its metric publishes as null, empty, rather than a fabricated number. Nothing scored is invented. One more discipline that saves us endlessly: a single naming rule. Every physical quantity has exactly one identifier, translated at exactly one seam. the adapter between the machine's controller and the engine. If a name drifts, it's caught at the edge immediately, instead of being discovered downstream and a dashboard 3 weeks later. Now, the direction most twins don't have, commands flowing back toward the machine. The twins' output on this path is an advisory ladder with 4 rungs. Nominal means run at 100% of commanded power. Caution derates to 80%. Warning cuts to 50. Critical commands 0 watts, a safe state. 4 properties that make that ladder trustworthy enough to demonstrate, and each one exists because we found the failure it prevents. It's ratchet proof. The rates apply to the commanded reference, what the operator asked for, never to the measured power. Without that rule, a derate lowers the measurement, the next derate compounds it, and the ladder walks itself to 0. Ours holds 80% at caution, period. It's latched and stamped. Once critical fires, it stays latched until a human resets it, and every command carries a timestamp and sequence number so the controller can enforce a 2-second staleness rule and ignore anything old. Gated. When the model itself reports low confidence, routine derates are suppressed, but critical always acts, because the emergency path must never depend on the model being sure of itself. And it's one round trip. Telemetry comes up and the command rides back in the very same response. Does it work? In the software in the loop testing on the hardware calibrated models in the lunar configuration, which is the only one where thermal runaway is physically possible, the open loop machine, with no twin, fires its hardware over temperature interlock 1390 seconds. The closed loop machine derates as the ladder climbs, latches the safe state on the forecast criterion, and peaks 73 Kelvin below the limit. The interlock never fires. Margin the twin created in the environment that actually threatens the machine.
This next slide is load-bearing for everything else we claim, so let us be completely explicit about it. Hardware interlocks are the sole fault authority on this machine. The emergency stop de-energizes the source in under a second. Microwave leakage and over-temperature interlocks read raw sensors directly. Stored energy shutdown is wired, not programmed. None of those depend on the twin in any way. If every piece of software we've shown you today crashed simultaneously, the machine protects itself. The twin sits strictly above that as an advisory layer, and every recommendation it makes carries its reason with it. Derate because a forecast is approaching a limit. Hold because the filter's consistency check is flagging that reality and model disagrees. And an attribution check, that check is a subtle failure. Power being booked to a chamber that isn't responding, which usually means a sensor or switching fault. Sequencing, which chamber runs when belong to the LabVIEW controller on the machine. The twin consumes the state as context. It never commands it, so the division of labor is clean. Safely lives in the hardware. The twin provides foresight, and just as important, it tells you when not to trust it. Now, since every proposal today says AI, let us be precise about what our machine learning actually is. And just as important, how it's kept on a leash. 4 elements. First, recursive state estimation. The unscented Kalman filter we described, recovering the hidden absorption state live, coasting gracefully through sensor dropouts, and continuously publishing a statistical consistency score. A number that says whether reality is surprising the filter more than it should. Second, a probabilistic forecaster. It doesn't just extrapolate a line, it propagates the filter's uncertainty forward through the physics and reports a timed event with a confidence band. It also accounts for the mass leaving the system as the material processes, which matters because a lighter charge heats faster. Third, the learned error model, the Gaussian process. Under 5-fold cross-validation, it explains about 89.5% of the remaining model error, plus or minus about 8%. But the design point is what it does outside its training data. It reverts to pure physics. It is never load-bearing. Conservation laws carry the prediction. And fourth and finally, bound parameter identification, the calibration machinery that fitted the metals chamber from bench data with holdout validation. All four together form a published, transferable gray box pattern. Physics provides the background. Learning fills in the gaps. It has earned the right to fill, and nothing learned can override the physics.
Here's an awkward truth about testing a safety system. You can't rehearse a real thermal runaway on real hardware. That would mean deliberately destroying the machine. So, we built ourselves a rehearsal stage. It's a synthetic truth plant, a physics simulation of the machine where we know the ground truth exactly, because we said it. It can play a nominal cycle, a runaway, a power loss, a seal leak, a slow sensor drift. Critically, it emits telemetry in the machine's real data format with simulated timestamps, so the entire live pipeline, from synthetic controller to the gateway to the engine to the dashboards, run exactly as it does with the real machine, and it stays truthful at any replay speed. This is not a mockup next to the system. It is the system, fed by a stunt double, and the numbers from that stage are current. In the Monte Carlo campaign that we've conducted, 48 randomized runaways on the hardware calibrated engine and the lunar configuration, with the truth physics deliberately scattered so the model never sees the exact plant it's estimating. All 48 were warned with at least 60 seconds ahead, with a median lead of 5 minutes, in other words, 300 seconds, and a worst case of 3.5 seconds. We resulted with 16 benign cycles, 0 false alarms, because a warning system that cries wolf is a system operators learn to ignore, and the whole build is pinned by 70 automated tests, 17 of which are adversarial, each one written from a genuine finding by an independent review. So every mistake we've ever made stays fixed.
How do we validate the models themselves? Continuously and statistically. Not as a one-time sign-off that goes stale. The filter carries a built-in lie detector, a statistic called the normalized innovation squared. In plain language, it measures whether the gap between what the model predicted and what the sensors delivered is the size the model claimed it would be. When the statistic sits inside the expected statistical band, model and reality agree, and we reevaluate it live during this very demonstration in front of you. Beyond that, held out validation, fitting on some data and testing on data the model has never seen in inflation studies, where we run physics only against physics plus learning to bound exactly how much the learned layer contributes. So nobody can accuse the machine learning of quietly doing the work. Before we ever presented this, we hired our own opposition. An independent red team went through the engine looking for ways it fails. Every finding they produced became a permanent regression test, and today's build passes 70 of 70. From here, the path to full hardware truth is a defined ladder. Tier 0 validates the power path, Tier 1 a single chamber, Tier 2 the full sequential cycle. And we've already taken the first rung. Metal's path is calibrated against 3 real cycle runs. One of them held out and predicted blind. We've begun on the second run. We've calibrated against initial plastic cycle. The reason you can trust this system is simple. We sent it to failure modes before you had to.
The last architecture piece is the conversation between the machine and the twin, and it genuinely is a conversation in both directions, live and the nominal scenario. The off-nominal scenarios run in simulation, which the challenge rules explicitly permit. Inbound, the machine's controller pushes timestamp telemetry through the Raspberry Pi gateway over an encrypted connection to the cloud engine. Outbound, a control command returns on every single ingest, carrying its timestamp, its sequence number, and the latch safe state, and the operator can push inputs the other way too, entering a weight mass or resetting the safe state latch after an event. And the engine describes itself. It publishes a manifest of 98 variables, every one with its name, unit, data type, and role, and convene binds the entire set by name from a single data source. That's what makes the digital thread real rather than rhetorical. The state, the requirement that constrains it, and the verification that checks it are all bound to the same names, all live. This is the seam we'll now show you working, and the command direction has a designed feature beyond what you'll see today. Commands will travel the same path as the data, in reverse, requested in the hub, passed down to the edge computer, written to the machine's controller over the same interface the telemetry uses, and applied within the controller's own bounds. Three tiers of authority keep that safe. Advisory commands the controllers may decline, operational commands it validates and executes, and safety actions that belong to the hardware interlocks alone, deliberately not commandable from software ever. And every applied command echoes back inside the next telemetry frames. So the thread verifies not just that a command was sent, but that it took effect. Before proceeding to our scenarios, it's important to show you what we actually have used to build the dashboards that will render up the data that we deem to be valuable to our system. What you are looking at is our digital twin orchestration workspace. This is the assembly line the twin is built on, from left to right. It starts with the systems model you saw earlier, and from it we define the digital threads, we configure the data and logic, and then we eventually compose that into the deployed digital twin, to where the data actually begins talking to the requirements and being rendered visually for stakeholder use. The twin is exercised against its various scenarios, and while granted we are still working out some bugs in logistics, the design and vision is firm. This serves as the gateway for closed-loop verification of requirements real-time as the system runs. A digital twin can be fully derived from its SysML model and built for stakeholder needs. So that's the architecture, and you've already seen its pieces live as we went. The real edge computer, the real engine, the real pipeline. We'll run the predictive thread through three complete scenarios. First, the nominal recycling scenario. Then the two NASA-defined off-nominal cases, the planetary surface scenario and a 5-minute total power outage. One framing note before we start. Why you're about to watch data and physics, not a 3D animation of the machine. That choice is deliberate and it starts from a customer question, not an aesthetic one. What does a stakeholder actually need from this system's visualization? Picture the moment that matters. The system is degrading and nobody knows why. This machine working is worth nothing in that moment because the failure isn't visible from the outside. This prototype is, functionally, a sealed black box, a microwave cavity you cannot see into, cannot put a camera into, and cannot open at 900 degrees. Everything that decides whether it's safe and efficient, how strongly the bed is coupling, how much thermal margin remains, how long until a limit, is invisible to the eye. It exists only as a recovered state, and that is exactly what we render. Here's what buys you in the moment that matters. The predictive engine detects a thermal runaway forming, but with lead time, a time to limit measured in minutes, not seconds. So the operator, or twin itself, throttles power back, and the system never experiences the event. That failure never has to happen on the real machine. The forecast layer that guarantees it is fully validated, and today it stands watch, silently behind every scenario you will see. That is what this visualization is for, and there's a deeper reason. Lunar infrastructure is critical infrastructure. There's no depot on the moon and no spare machine on the next flight. What the customer needs is longevity, a system that fulfills its entire life cycle, with sustainable maintenance, keeping it from falling apart, running at maximal efficiency the whole way. At its highest fidelity, this system runs as an automated fleet. Feedstock in, product out, no human in the middle. A virtual reality walkthrough serves as a tour guide. Data analytic visualization serves the operator who has to keep a fleet alive for years. We built the interface that matches the mission. This does a whole lot more than visualize. It ensures safety, and it keeps the system at maximal efficiency for the entire duration of its life. One piece of candor before the live portion. Convene is a pre-release platform. Reclaim is its first full end-to-end deployment, as some of what you'll see is genuinely being shown for the first time. So if you catch a rough edge in the interface, that's the alpha showing, not the twin failing. The architecture underneath, the predictive engine, and the live thread are real and running right in front of you now. We'd rather show you a real system early than a polished mock-up of one. Two more sentences of scope so you know exactly what you are watching. First, the data. For the purposes of this online demonstration, the telemetry stream is hybridized. The physics coefficients inside were fitted from our real hardware runs, and the cycle profiles are idealized to the machine's expected nominal behavior, so the scenarios play the way the flight system is designed to run. Second, the command path. The bidirectional design is final. You will watch the engine compute and publish a control command on every single frame, and the execution of the final return leg into the machine's own controller is still in work. The full closed loop, hub to controller and back, is what we will demonstrate in person at the demonstration in Tuscaloosa, Alabama in August. We begin at the system's resting rate. What's on the screen now is idle. Both chambers live and streaming real telemetry at ambient temperature, about 22 degrees Celsius on the pyrolysis bed, 24 on the smelt crucible, with 0 watts commanded. Notice the readings are moving, just slightly. That's because this is a live feed, not a screenshot. The machine is on and resting. Every scenario today starts from this date and returns to it. On pacing because we respect your hour. Each scenario you'll see plays out in about 5 minutes. These are 30 to 60-minute processes in real life, so the feed runs on an accelerated clock, and because every frame carries its own simulation timestamp and the engine integrates on the telemetry's clock, acceleration compresses the waiting without touching the physics. What you'll watch is truthful at any speed. Scenario 1. The nominal recycling cycle. A normal, successful day for this machine. Here's what a cycle is. The single microwave source runs two paths in sequence. First, it melts a 500-gram charge of aluminum in the smelt chamber, then the power switches over and it pyrolyzes 500 grams of polyethylene in the plastics chamber. One chamber, two processes, time shared. That's the machine's whole trick, and the twin tracks every phase of it. As this runs, notice what the twin is doing and isn't doing. It's phase aware, not phase driving. The live view controller on the machine owns the sequence. The twin consumes the operating state as context and keeps estimating and forecasting continuously alongside it. And everything you see scored, the efficiencies, the thermal margin, the cycle duration, is computed live from this feed, with its provenance attached. Nothing on this screen is pre-rendered, and nothing scored is fabricated. As we said up front, the design is final. The execution of the last return leg into the machine's own controller is still in work, and the full closed loop, hub to controller and back, is what we will demonstrate in person. When the cycle runs, let's name 4 things on this screen that the hardware alone can never give you, because this is the value proposition of the entire twin. First, continuous stress forecasting. The twin is always answering the question, how long until trouble? A quantified time to runaway with a confidence band, recorded minutes before any limit is threatened. The machine simply does not produce that information. No sensor measures the future. Second, hidden state estimation. The absorption behavior of the silicon carbide bed, how greedily it's drinking microwave energy right now, is being recorded live by the filter. Again, there is no sensor for this. It's inferred from the physics and the measurements together. Third, explainable health monitoring. The twin runs a continuous audit. Does the energy balance close? Is the coupling drifting? Is the seal holding? Is power going where it's supposed to go? Each check reports its reason, so an anomaly arrives as a diagnosis, not a mystery alarm. And fourth, live verification with a trust score. Requirements, margin, efficiency, consistency are verifying themselves against the live state as the cycle runs, right next to a trust score that the command path respects. The twin grades the machine and grades itself at the same time. Now, the first off-nominal case, the one NASA defined, operating on the lunar surface. In this scenario is where conservation law architecture really pays its rent because of how little we have to change to get there. We change one block, the environmental loss term. Gravity drops to 1.625 meters per second squared. Pressure goes to near vacuum, and with no air, there is no convection. Heat can leave this machine by radiation only. Everything else, the physics, the estimator, the thresholds, the requirements, is untouched. And the hardware calibrator results reorder where the risk actually lives. The runaway crossing itself barely moves. 1,343 seconds on Earth versus 1,390 on the lunar surface. Later, not earlier, because near the operating point, the cooling is already radiation dominated. And with the charge loaded, the chemistry of pyrolysis blocks runaway outright in both environments. The danger window only opens once a batch is spent. Where the moon truly bites is afterwards. With radiation as the only exit for heat, the half cooldown from 900 Kelvin stretches from about 970 seconds to about 1380, a 42% penalty on every cycle's turnaround, on handling, and how long the machine stays dangerous after shutdown. So the operational risk concentrates on the moon, which is exactly where the off-nominal you will see the next matters most. Take a moment on what this is. A defensible physics-derived prediction about a condition that no Earth prototype can ever be physically tested in. That is the promise of a digital twin delivered. Our second off-nominal is the one operations will actually mean, a total power outage mid-batch. On the lunar surface, power is the single most fragile utility. Eclipse, load shedding, a trip bus. And no technician is standing by when it happens. An interruption is not an anomaly, it is a certainty. And the question is whether your systems keep their heads. Twin does when the lights go out. Nothing is scripted. The power simply stops at 50% of the plastics batch. The plant coasts on its own physics, and the twins estimate to coast with it. The free thermal decay you will watch is a live audit of the very lost coefficients we fitted against the hardware, tracked within sensor noise for the full 5 minutes. The operating state flips to cooldown on its own. Nobody tells it to. The classifier reads power 0, bed hot, temperatures falling. And remember, the planetary result you just saw. On the moon, the same physics stretches every recovery by 42%. This exact scenario is where that finding cashes out. Now watch what the twin does not do. It does not flinch. The advisory ladder stays at nominal end to end because a machine coasting unpowered is consistent physics, not an anomaly. A warning system that cries wolf during a benign blackout is a system operators learn to ignore. When power returns, the restart ramps in softly and the batch runs to completion, and the cycle closes. Composure under interruption is a design capability, and behind it, the validated runaway forecast layer stands guard the whole time, on every one of these cycles.
So what does the engineering program actually get? The twin is an instrument, not a display. Every run you just watched feeds the next design revision. The fitted loss coefficient sizes, insulation, and wall geometry, the planetary results, locates margin erosion, and the cooldown costs before flight hardware exists. The recovered absorption feedback sizes the subceptor and shapes the power schedule. And the live mass and energy counting points at the next efficiency gain by name. Form, fit, and function, informed before metal is ever cut for flight. And that is not hypothetical. The first real calibration campaign already returned a design decision. The bench data shows the subceptor coupling almost instantly, while the bulk charge lagged hundreds of degrees behind. The melt is limited by heat spreading into the charge, not by generator power. So the next revision buys more from thermal spreading than from watts. 3 bench cycles in the twin already redirected the design. And at mission scale, that is what sustainment looks like for lunar infrastructure. No depot, no spare machine on the next flight. The twin is how the system stays safe, maintained, and at maximal efficiency for its entire life cycle. Two words we want you to leave with: accuracy and cohesion. On accuracy, the core is conservation law physics. Coefficients calibrated against log cycles. Now, including real hardware runs, with instrument uncertainty entering honestly as measurement noise. The headline on the hardware calibrated engine, a runaway, crossing predicted 304 seconds ahead, accurate to about 8 seconds. With the filters statistical consistently, check running live during the ferry demonstration. On cohesion, there's one model. CAD volumes become the model's heat capacities. The measured channels are themselves the verification objects. In the off-nominal scenario are the same equations with one block change. Computation, model, and requirements are one deployed object. Accuracy you can measure, cohesion that's structural. Let us close by putting the pieces back together. The forecast is mechanistic. It comes from the absorption feedback physics, not a pattern matcher, which is exactly why it stays valid in conditions as never seen, including a lunar case. No prototype can physically exist. Across the recalibrated Monte Carlo campaign, 48 runaways out of 48 were warned, with a median lead of 5 minutes and 0 false alarms. The verification is closed and continuous. Requirements
bound to the live state, verifying themselves in the thread during the run. 70 of 70 tests green in the build you just watched. Reclaim demonstrates the physics predictive digital twin can be assembled over a program's existing engineering data. Its CAD, its requirements, its telemetry, and deliver a true anticipatory understanding. Honest about what it knows, predictive where it counts, cloud native, and reusable for the next system after this one. For infrastructure that has to live on the moon, that is not a visualization feature. It is how the system stays safe, stays maintained, and runs at maximal efficiency for its entire lifecycle. Thank you.